Yeah, with Aero, I think there are people that are like super passionate about it. I think Dr. Myral is one of those people, and so yeah, he's kind of on a whole different level.
Yeah, it's really fun.
Mhm.
It's a lot of work that I have to do.
Mhm.
I think that's what the struggle is. Like if it was required, I'd be like, all right, cool, let's get it done.
Mhm.
But since it's just an elective, I'm like, oh, should have taken something easier. So based off of everyone I've talked to so far, not a single person could do problem 4 of the homework assignment this time.
Wait a second.
Problem 4 of your homework.
Oh yeah.
No one I know can do it.
I've talked to a few people about it. It's tough. And I designed that problem in a way such that you kind of tinker with the parameters. But it's like I mentioned in class too, that it's for some circuits and for some targets, it's impossible to hit everything correctly.
Okay.
And that's just kind of the nature. That's kind of the limitations of the LPMs too. And so I've been telling people, just do your best. You know, I mean, for this class, you know, I just grade the homeworks on completion anyway. And so as long as I see that you put an honest effort into it, and that you get closer to the targets compared to before, that's good enough for me.
I haven't looked at the problem yet. I'm guessing it's like a tuning problem.
Yes.
Yeah. Okay.
So it's a lot of trial and error, and so you're going to basically tinker with the parameters and then see how it results, and then so people have gotten pretty close, actually. You know, I think it's the last target that's been tripping people up. But you know, as long as you get closer and you know you give an honest effort, then that's all that matters to me. You guys, how's it going?
Very well. Yeah.
Good, good. It's my last class before spring break, so I'm excited.
Sorry, I had something to ask you. It's like I'm gonna throw down a clash right now. Honestly, like the minute like I have so much crap to do, and I like ran to the library to work on it, and as I was walking away, a bunch of people were like, "Clash." I'm like, okay. I got in here like an hour early. One problem for you. It's not like it's just not correct. Oh, I like a shirt. Oh, no, I really like it. Where'd you get that? Swami. Okay, I gotta go. I'll go on vacation too, right? I literally just said I'm from 3. One from 3. I'm from 3 and from 4. Just the math upset. How's that class going? Rough? That's the 3 added videos. Wait, no, that's interesting. Yes. I was talking about 4.8. 4.80.
All right, it's 4 o'clock, so let's go and get started. All right, good afternoon, everyone. It's our last day before spring break, so how's everyone doing today? Yes, clap, 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 yes. I'm just as excited for spring break as you guys. It's man, I'm tired today. It's been a eventful week for stuff that you guys don't see, but it's been an eventful week behind the scenes, that's for sure. Oh, I have a headache. Man, take some Tylenol. Hopefully that'll make it feel better. Whenever I tell my best friend from high school that I have a headache or something like that, he's like, man, just pop a Kylie Jenner and then you'll feel right better after that. Okay, so it's our last day before spring break, and so we have a little bit left over from our lecture notes on 1D equations, mostly just the MATLAB code, and so I want to show that to you just to kind of illustrate a lot of the ideas that we were talking about, because we spent basically 2 whole lectures doing some very intense mathematical derivations, and so I want to give you guys some payoff for that. So I want to show you guys what all that was for. And then from there, we're going to move on to our next set of lecture notes, which is called impedance. Okay. And so our impedance lecture notes are going to build directly off of what we talked about here, kind of give you a little bit more context on what this whole wave reflection thing is. Okay. because we've talked about wave reflection, and I think we at this point we kind of have a good understanding of what it is. But I think hopefully with the next set of lecture notes, you'll have a better understanding of why it happens and why it's such a complex phenomenon that occurs in our cardiovascular system. Okay. All right, and so remember the homework is due on Friday, and so I know quite a lot of people have been working on it. I've gotten quite a few questions on problem 4 of the homework, which is the tuning problem. And so, for the tuning, I know it can be really difficult to tune the parameters such that you match every single target exactly. And that's not the goal that I want you guys to do, right? So remember what we talked about when we did LPNs, that sometimes it's just really hard to hit those targets, because sometimes you have 3 targets, you have lots of parameters in your system, and so even if you tinker with those for a really long time, it's hard to get them to match. And so I want you guys to focus less on trying to hit the targets exactly. I want you guys to focus more on just trying to get a feel for when I have an LPN like this and I play with this parameter, right? So I increase the parameter, decrease this parameter, whether it be a resistance, a capacitance, and inductance. I want you to see how that affects your results, okay? And so, for B in particular, I know I'm asking you to, to hit 3 targets, but I gave you 3 targets for that just so that you can see, when I tinker this capacitor, what does that do for this target, but also what does it do for the other targets as well, okay? And so if you're not able to hit all the targets, that's fine. It's not, I'm not grading this for accuracy. It's more just it's an exploration exercise. And so I want you guys to explore those parameters, see what they do, and then do your best to hit the targets as closely as you can. Okay. Okay. And so I think that's all my announcements. And so I think there's a couple people in the class who still need to choose their final project topic. And so if you haven't chosen your final project topic, please let me know as soon as possible, so I can get you your image data, and then then you can start working. Tomorrow I might start actually individually reaching out to people just to make sure that you guys have all that information. All right, and so that's all my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and pick up where we left off. And so on Tuesday, what we were doing, and so we're still on this topic of the 1D blood flow equations. Right. And so if you recall, our 1D blood flow equations were these partial differential equations that we can use to solve for the area, the pressure, and the flow rate in a blood vessel. Okay. And most importantly, we derived these equations in such a way that allowed us to solve for these quantities along the centerline path. Okay. Okay. And that's really the key point. And so, that's where the one-dimensional 1D and the 1D equations come from. That one dimension is down our centerline coordinate. Okay. And so if you had a vessel that looks like this, right? And so I draw kind of curvy on purpose so that, just to kind of illustrate to you that, the centerline path kind of follows the curves of the vessel just like that. And if we do that, we would get, we'd be able to solve for the flow, pressure, and area here. Okay. But we could also find it at any other point along the vessel as well. Okay. And so it could be just wherever we want. And so this gives us a lot more flexibility. And so, I know a lot of you are working on the lump parameter homework. With the lump parameter models, you're only able to solve for these quantities at distinct at discrete locations within the circuit. Okay. With the 1D equations, you kind of have the freedom to solve for these wherever along the vessel that you want. Okay. All right. And so we spent, the last two classes deriving their expressions. And so what I want to do, before we close up this this chapter, is to show you how this is applied to a simple vessel. Okay. And so our vessel looks like this, or at least its centerline path looks like that. On the left here, we have the inlet. On the right here, we have the outlet. Okay. And some of the properties that we're going to specify for this vessel are going to be its viscosity, nu. We're going to specify its density, rho. We're going to specify its base radius, okay, r. We're going to specify its Young's modulus, E, as well as its wall thickness, H, okay? And we'll set all these in the code. And so, we don't have to worry too much about this, okay? Into the vessel, we're going to specify a flow rate, okay? And so this is going to be a function of time, okay? Q of t. And for this vessel in particular, I remember I'm kind of borrowing this code from a colleague of mine. What he did was he actually took a real person and he measured the flow rate of blood in their carotid artery. And so this is actually taken from real data. Okay, and so it's real data for for this. And so we took a peek at it last time in MATLAB, but let me go ahead and just draw it again. Okay. Right, so the Qn function looks something like this. And so we come in, we have a little bit of a dip, then we go up, then we come down, then we have a little bit of an oscillation there at the tail end. Okay. Okay. So that's the situation that we're going to simulate with our MATLAB code. Okay. So the MATLAB code, itself, there's a lot going on to it, and so I don't want you to get too caught up in the details, but I do want to kind of highlight some key features of that code, just so that if you want to tinker with it, if you want to kind of run it under different conditions, then you're able to do it. Okay. Okay. So that was just kind of a recap from last time. So are there any questions on any of this? Okay. Okay. And so with that, let's just jump into the code. And so let me go ahead and bring up the code here. So let me go ahead and share my screen. All right, so here is the code. And so if you download this code from Canvas, it appears as a zip file. And so if you go to our home page, okay, and you go to week 9, you'll see that there's a link here for a zip folder called carotid.zip. And so you need to download everything there, because inside that folder is going to be several different files. And so these files, each of them are used for different purposes. And so some define the inflow, some define the linear solver, some define the outlet boundary conditions, and so on and so forth. But the only one that you really need to look at here is the carotid.m, which is the main. You can almost think of as like the driver code for this, for this folder. All right, so let's go ahead and open up this file, and you're going to see a ton of code here. Okay, but we're only going to focus on the parts where we can actually make an impact on the results. Okay, and that field right here is this field right here, where we get to define the fluid, material, and geometric properties. Right? And so, this code, I'm giving you this code, not that I expect you to, understand everything that's going on here, because it's kind of a lot, but I do want you to be able to, modify it to be able to view different different phenomena. Okay. So let's go through each of these parameters and see how they match up with our 1D equations. All right, so first thing we have is mu here. Okay, so this is our viscosity, and so the units for this is centipoise. Okay. Next we have rho, which is the density, and so that is 1.08 grams per centimeter cube. Okay. Right. Next we have a reference pressure, PD. Right. And so that's kind of like a background pressure, and so that's kind of like a reference pressure for our system, just to make sure that our vessels are properly pressurized. Okay. Next, we have the radius of the vessel, and so this is the base radius, and so as if if the vessel didn't have any kind of pressurization, this would be its radius. And we also have the length of the vessel. And both of these quantities, the length and the radius, are given in centimeters. Okay. And then lastly, what we have here are some of the material properties of the wall itself, right? So this is not the fluid, but the solid wall that surrounds the blood, right? So we have the Young's modulus of the wall, which is given by E1, and then we have the thickness of the vessel wall, which is H1. Okay. And so before we modify anything, I'm just going to go ahead and run this code. And that's going to give us a couple plots here. Right, so it took about 13 seconds for our simulation. Okay, and here we have the resulting plots. So there's two here, and so let me go ahead and kind of explain what's going on with each of these plots. Okay. All right, so the first plot here, I think that's the one we started talking about, and so that's the flow waveforms. And the way these plots are formatted is that they're not measuring the flow as a function of space, but they're measuring the flow as a function of time. Right? And so you can see we have two plots. And so one is at the inlet and one is at the outlet. So if we draw kind of our 1D vessel just like this again, okay. So what this is measuring is, what is the flow rate at the inlet? And so the inlet, of course, is where the flow comes in. Okay. And then we're also measuring the flow rate at the outlet. And so this is out here. All right, and so let's talk about some of the differences between these two curves because they're obviously not the same, right? And so we have some differences in between them. All right, and so normally when you have a rigid vessel, right? So you have a rigid tube, and you input a flow into that tube, right? What you should get in that tube is that the flow rate is the same everywhere in that tube, right? Because the walls are rigid, and so if you input a certain amount of mass, then that mass has to come out, and so there's no way for that mass to be stored within the tube at all. Okay. Here we don't have that, and so you can see here we have a difference between the flow waveforms at the inlet and the outlet. And so I want to kind of draw to your attention to two different regions. So we'll first look at regions where the blue is higher than the red, right? And so that's right here. And then we'll also look at sections when the red is higher than the blue, which are mostly these tail sections right here. Okay. And so let's talk about the section when the blue is higher than the red first. Okay. And so that's when the inlet waveform in blue is a lot higher than the outlet waveform in red. Okay. Remember when we talked about the Windcastle model? And so the Windcastle model for blood vessels states that when the heart is pumping or when the heart is contracting, right, then what's happening is that the blood vessels are inflating, right? And so basically you're going to get a huge rush of blood flow from the heart, and so that rush of blood is going to come in, and because it's so much blood at any given time, then the vessels themselves are going to inflate. Okay, so kind of like a balloon. They don't inflate fully, and so there's still some flow that comes out the outlet, but it's not the same amount of flow as the inlet, and so there's a difference between these two, right? And so that's what you're seeing here. And so because the blue waveform is higher than the red, that basically tells us during this phase right here, the vessel is inflating. Because we have more inflow of mass compared to outflow, right? And so that difference, basically this difference in between the two curves, that's basically the amount of volume that the vessel is inflating by. All right. And so of course, if when the blue is higher than the red, that means inflation. then the opposite is true for the other parts. And so for the parts where the red is higher than the blue, this is, of course, when the vessel is deflating. Okay. Okay. Because those are parts when we have more outflow than inflow. And so, the vessel overall during these times is losing mass compared to the inflow. And so if it's losing fluid, then there must be a net decrease in volume. And so we call that deflation. Okay. Now, if only the economy would deflate, that would be great. Okay, and so I think that's kind of what we talked about at the end of class last time. But I want to make sure I emphasize this, because this is I think one of the most clear ways that you can see that of how inflatable, or excuse me, deformable walls have an impact on these flow waveforms. All right, any questions on this? Okay. All right, so that's the flow waveform. So now let's talk about the pressure. Okay. And so for the pressure waveforms, you can see that we have two curves. And so we're using the blue and red convention as before, inlet and outlet. Okay. And you see the two curves are fairly close to each other. So they have, they reach about the same peak, and their minimums are almost the same. So they're slightly different, but not quite the same. Okay. But there is a little bit of offset, so they're not completely on top of each other, right? Again, the fact that let me draw the vessel again. Okay. The fact that we're not guaranteed to get the same pressure here at the inlet versus here at the outlet, again, is a direct result of the deformable walls. Okay. Because if the walls are rigid, then that means that the pressure waves would propagate at infinite speeds. And so any change in pressure that occurs at the inlet, that would instantly propagate to the outlet, and then these two would be at, basically in sync with each other. Okay. And so the fact that there's, a difference between them, again, is due to the deformable walls. And in fact, one way that you can interpret that is that the red curve, the outlet, it's a little bit delayed compared to the inlet, right? And so you can see that it starts to swing up a little bit after the inlet one, okay? And so this delay here is due directly to wave propagation. Okay? And so what's happening is that the pressure waves, the pressures are changing in the vessel here, but that pressure wave takes a little bit of time for it to travel down the length of the tube. Okay. And so because we have pressure waves that travel at finite speeds, then that's a direct result of our wave propagation. Okay. And so let's see what happens when we modify some of these parameters. Okay. So kind of remember what these curves look like, and let's play with some of the parameters here to kind of modify what it looks like. Okay? And so the first thing I want to modify here is let's modify the length. And so let me go ahead and change the length right here. Let's change it to something much smaller. So let me change it to 5. Okay. And so now we're running this basically the same simulation, but with a much shorter vessel. And so let's see what that does to our outlets here, our outputs. Okay. All right. So with the much shorter vessel, let me go ahead and bring these here. With a much shorter vessel, you can see that the curves come a lot closer to each other, right? And so if you remember from our vessel with a length of 12 centimeters, there was a pretty significant difference in between the red and the blue curves. But when we shorten that vessel up, when we only make it 5, then these waveforms become a lot closer, right? And that makes a lot of sense because with a shorter vessel here, there's a lot less space or a lot less volume, if you will, for it to inflate. And so there's a lot less flow that's going to go towards inflating the vessel, and most of it's just going to flow right through. Okay. Same thing for the pressure waveform. So for the pressure waveforms, you can see that we still have a little bit of a delay here, but because we shortened up the vessel, we basically minimize this wave propagation phenomenon just because there's just not as much space for the waves to propagate anymore. And so the wave's going to travel very quickly down the vessel and hit the outlets, when they do. All right. Any questions on this? Okay. All right, so let's make one more modification. So I'll keep that the same. And so let me go ahead and actually let me trick this back before. So before this was 12.6. So let me go ahead and run it one more time just so that we etch the curves into our mind. Okay. And so this is what the curves look like when the lengths are 12.6. Okay. And so let me take the same vessel and let me increase the Young's modulus. And so what I'm going to do is I'm going to triple it. So I'm just going to do 3 times this. Okay. Right. And so remember, the Young's modulus is a reflection of how stiff the vessel walls are. So the higher the Young's modulus, the more stiff or the more rigid the vessel walls are going to be. And so this is, you know, you can kind of think of this as a way to simulate how an older person's blood vessels would perform. Right. Because remember, one thing that older people do is that their blood vessels just kind of get naturally a lot more stiff compared to younger people's. Right? And so with a much stiffer blood vessel, let's go ahead and run the code. Okay. Right. And you can see here that the differences are pretty clear, right? And so with the stiffer blood vessel, right? And so think about a balloon. And so if you make the balloon a lot more stiff, you know, it's not going to be able to inflate as much as before, right? And so we get kind of the same effect as when we shorten the blood vessel, but now this is with the longer blood vessels before. But you know, because the Young's modulus is a lot higher, you know, we don't get as much inflation effect, and so the inflation effects are minimized, and you see that the 2 flow waveforms are roughly the same. Okay. But the pressure actually didn't change too much, and so the pressure is you know, basically the same as the 12, you know, before when we stiffened up the vessel, and that's because, you know, this vessel is you know, the main determining factor that affects the pressure wave propagation is kind of the length of the vessel. Okay, and so the material properties, you know, they do affect the wave speed to some degree. But I think for this kind of vessel right here, because the length is already so small, then, you know, any changes to the wave speed, you don't really see it manifest in the pressure waveforms. But you do see the difference in the flow waveforms, you know, pretty clearly. All right, and so you know, that's the 1D code, and so I've left that code up on the website, and I think on the next homework that I have planned, you know, I'm going to have you play around with these numbers as well, and have you kind of explain some of the differences that you observe. Okay, but you can go ahead and download that. You can go ahead and play around with the values if you want, and that's it for our 1D equations. So are there any questions on any of this? All right. And so I'm really thankful for my colleague here, because the other 1D code that I've worked with before is not as friendly as this one. So it's a very lengthy kind of C++ Fortran code, and it's not as easy to use. Yeah, question.
So the code only represents like the healthy vessel.
Yeah. So that blood vessel, I think the numbers were for a mostly healthy person, but you can change those numbers for a diseased person as well. And so you can make it so that, you know, that you can play around with the stiffness of the vessel wall. You can make it a lot more loose than before, and you can make it a lot smaller too. So one parameter that we didn't modify was the radius. And so if you want to simulate like atherosclerosis, and so you can make the radius a lot smaller, and you can see how that affects the flow and pressure waveforms as well. Yeah. Okay. All right. So the next topic that we're going to go over is called impedance. Okay. And the cool thing about this, and I don't think we'll get to it today, just because, you know, but after the break, we'll actually be able to use some of these techniques to analyze not only just single vessels, but actually networks of vessels. And so I think that's kind of the cool thing about this as well. All right. And so, you know, before I begin, you know, let's kind of remind ourselves about the concept of a resistance in fluid mechanics. Okay. So we've been talking about resistance a lot in this class. I mean, first of all, very explicitly once we did the LPNs, but we've kind of brought up the concept, here and there. We talked about biomechanics and everything, right? And so our resistance, you can even visualize it as like a resistor, right? What the resistance does is that it measures the viscous friction resistance to flow. Okay. Okay. And so I think the best analogy here is it really is friction. And so when you try to think about when you try to rub two solid objects together, right? Sometimes it could be really hard because if the amount of friction in between the objects is very high, so you're trying to rub sandpaper on on other sandpaper, so sandpaper on sandpaper, that's pretty hard to do because the amount of friction there is really high. And so the fluid mechanical kind of analog to that is viscosity, viscous friction. Okay. And I think the easiest way to kind of visualize that to work with it in calculations is as a resistance. And so when we talk about resistance in fluid mechanics, what we're really talking about is viscous friction. Okay. And so I think that's kind of a good first analogy, I think, when people are first introduced to the idea. But it kind of oversimplifies it a little bit, okay? And so this whole idea of viscous friction and in fluid mechanics is a little bit more nuanced than kind of what you expect from solid mechanical friction. In particular, what we'll see, what we're going to see is that this the amount of opposition that you get for flow inside a vessel, of course, it depends on the viscosity. But what you're going to see is that you're going to have different amounts of opposition depending on the frequency of the flow. Okay. Okay. And so what do I mean by frequency? And so, when you think of frequency, you think of some kind of oscillating wave or some kind of sine wave, right? And so if we have a wave that looks like this, right, versus a wave that looks like this, right? We can see, just visually with our eyes that the second one has a much higher frequency. Okay. And we can see that because it oscillates a lot more. And so you can see it goes from the peak to the valley, much faster than the right one. Okay. And so if you have steady flow, and so you have no oscillation at all, you don't really have to worry about this idea of impedance because you can just measure the resistance just based on that steady flow. Okay. And that's what we did when we did our review of fluids, right? And so when we solved our cylindrical Navier-Stokes way back in, I think, the second or third week, we assumed, first of all, we assumed that the walls were rigid, but we also assumed that the flow was steady, right? And so because the flow was steady, then we did have that formula for resistance, right? And so we had some formula when flow is steady, right? I don't have it off the top of my head, and I don't have it in these notes, but it's some like 8 pi nu divided by pi r to the 4th, something like that, right? So that's great if your flow is steady. But in the cardiovascular system, you know, we don't have steady flow. We have flow that's pulsatile. Yeah.
So I'm just curious for problem 2 of the homework that I prompted. It asks you if you can accurately find the shear stress.
Yeah.
And then based off of this, so I thought the answer was no, and I gave my belief because it's not a rigid body, it's flexible. And I couldn't find it in notes just based off of my own thoughts. Looking at this, it says you can find the friction. I'm guessing you can find the correct friction, you can find the correct shear stress. But at the same time, if there's different frequencies, then that makes it more complicated for finding the shear stress. So what's the answer? Could you accurately find it or not?
So the answer is no.
Okay.
So it's due to a variety of factors. And so you hit on a lot of them already.
Okay.
But the other one that I'm also looking at for that one is for lump parameter models. You know, we don't have any idea what the velocity profile looks like, and so we're approximating just as a flow rate Q. And so if you remember from our lecture on fluid mechanics, right, the shear stress, the formula that we have for it, that's not shear stress, that's viscosity. And so the shear stress is equal to the viscosity multiplied by the velocity profile, right? And so we don't have any velocity information in LPNs. And so we can make some assumptions about what the velocity looks like, but a lot of times we don't really actually know. And so due to all those reasons that you mentioned, but also this one, then I wouldn't trust a shear stress from an operator.
Okay.
Yeah. Okay. Right. So you can get resistance. You can get a formula for it if you have steady flow and rigid walls and, you know, a bunch of other assumptions. You know, but we don't have that luxury in cardiovascular flow. And so, you know, instead of talking about resistance for pulsatile flows, what we have instead is this idea of impedance. Okay. And so impedance, the idea of impedance is that we think of it as like a resistance in the same way that we think of resistance, is that, you know, impedance is still measures in opposition to flow inside our blood vessel, but it has a lot more factors that go into it. Okay. And I really struggle with spelling. I'm part of that generation that's been spoiled by spell check, and so, you know, I don't know how to spell. The boomers were right in this case. Okay. And so when we think of an impedance, how old am I? You're right there. Why don't you ask me? I'm 31. Why are you typing in the chat when you're right here?
That was an awkward question. So.
I see. I understand. And so, you know, we're going to talk about impedance a lot in this lecture, but, you know, I don't want you to think of it as something separate from resistance. Yes, it's a more nuanced version of it, but when we think of impedance, you know, we're still talking about an opposition to flow, and viscosity is still going to play a huge role here, but, you know, it's just a little bit more nuanced because it takes into effect, you know, a lot of these things. And if you, I don't know if they cover, I should really look into see what's covered in the circuits class here. And so did you guys cover impedance in your circuits class before, or when you did Laplace and things like that, Fourier? Kind of. Okay. So you're kind of familiar with the idea. So we're going to kind of transform a lot of those ideas to fluid mechanics here. And so, you know, that's good. It's good you guys are kind of familiar with it. Okay. and kind of the goal for this is impedance itself is really interesting, and I think it's important to know. But kind of the goal for this is to get a better understanding of the wave propagation, and also the wave reflection phenomena that happens in the cardiovascular system. Okay. Right, the wave reflection will be particularly interesting because I think up to this point, we know that pressure waves, they reflect in the cardiovascular system, right? So we send pressure waves from the heart, it reflects and comes back eventually, right? But we only really talked about reflection when the flow reaches the very end of the tree. And so once the flow reaches the capillaries, that's when the pressure waves reflect. But what we'll see, through these notes is that there are other places where the pressure waves can reflect. Okay, and so it's not necessarily just at the capillaries. Although that's where kind of the effect is most pronounced. But what we'll see is that whenever you go through a change of impedance, and so whenever you have flow going through a certain vessel, but then it starts to go to another vessel with a different impedance, you have some degree of wave reflection that occurs there. Okay, it's not a complete wave reflection, so it's only partially, but that's kind of what occurs. All right, and so that's kind of the motivation and kind of the groundwork of why we're diving into this idea of impedance. So, there are any questions on this? I've always had trouble with spelling ever since I grew up. My advisor makes fun of me, although this is her fault too. I have a spelling mistake in the title of my dissertation. Actually, I spelled modeling incorrectly, and then she didn't notice until my defense, and then she just like, "Oh, your modeling is spelled incorrectly." It's like, wow, yeah, thanks, Allison, for embarrassing me in front of my entire committee and my family and my friends. Okay. Was that?
Such a great friend.
It was my advisor. Okay, so before we can talk about impedance, we actually have to return to our 1D equations because that's going to give us the mathematical basis for studying impedance. Okay, and so let's go back to the 1D equations, but we're not going to look at the 1D equations in its full complexity. Because as you just saw at the beginning of class today, you need a MATLAB code to just solve those equations. And so what we're going to do instead is we're going to take the 1D equations and linearize it. Okay. And so linearization, it's a very common thing that people do in applied math. Basically, the idea with linearization is that you take a complicated equation. It could be a differential equation. It could be an algebraic equation. And you just make it simpler by making all the terms linear. Okay. So I will say that this linearization, I did learn some of it when I was an undergrad, but it's definitely much more of a graduate topic. And so we're going to go through the math about it just so that you can see it. But this is one of those things where we're going to go through the derivation, but I kind of want you to just kind of keep the big picture in mind as we go through it and not really get lost in the weeds of the details. And the main way that we get a simpler equation is by taking all the nonlinear terms in the equation and basically linearizing or making them simple. Okay. So let me show you what I mean. And so let me write out the 1D equations again. And so first we have a conservation of mass. So we have partial A, partial T plus partial Q, partial X. Okay. So that's going to be equal to 0. So that's conservation of mass. So there's nothing wrong here. And so conservation of mass is already a linear equation. And so we don't have to do anything to it. Okay. The momentum equation, on the other hand, has quite a few nonlinear terms. Okay. All right, so that's our momentum equation for the 1D equations. Okay. All right, so in particular, let me go ahead and highlight some of these terms. Okay. So I'm going to highlight this one. Okay, that one's very nonlinear. This one's also nonlinear. And this one is also nonlinear as well. Okay.
What's the top equation again?
The top equation is conservation of mass for our 1D equations. Okay. And so all the terms that I've circled here, we call those nonlinear terms because they involve the product or quotient of the terms that we're trying to solve for. Right? And so remember, in the 1D equations, we have three things that we want to solve for. And so we have the flow rate Q, we have the cross-sectional area A, and we also have the pressure P. Right? So those are all the things that we need to solve for in these equations. Okay? And whenever you have a mathematical expression where you have products of these, then you have a nonlinear equation. Okay. Right. And so if we look at the first term that I circled, and so we have a partial z of 4/3 q squared over a, right? And so to get q squared over a, another way that you can express that is do q multiplied by q, okay, multiplied by a to the -1. Okay. So this term is actually very nonlinear. And so first of all, you have q squared. And so whenever you have something squared, that's automatically nonlinear. And so that's a red flag already. But we also are dividing by a. And so that dividing by a also makes this nonlinear because you have a, even if it's by itself. And so you have 1 over a by itself. This is already nonlinear because you're taking a and it's in the denominator instead of the numerator. Okay. So this term, very nonlinear. So we're going to have to do something about that term before we can actually solve. Okay. The second term that I've circled, it might look linear at first because it doesn't, it seems like we only have a up top, right? We divide by the density. The density is a constant, and so we don't have to worry about that. Okay. And so it might seem like this term is linear because we just have an area, but we're also multiplying by the pressure derivative. Okay. And so effectively we have an area times the pressure. And so that product in between the two makes it nonlinear as well. Okay. And then the last term, you can see that's nonlinear because we have a q over a. And so because, first of all, just by dividing by a, that makes it nonlinear. But the fact that we have both q and a
And the exact same term, makes this a nonlinear expression. Okay. And so when we linearize this equation, we have to kind of get rid of these as much as possible. Either get rid of them or put them in a different form that makes it easier to solve. Okay, any questions on any of this? Okay. All right. All right, so to linearize this, one common way to do this in applied math is to define what's called a reference state. Okay. And so a reference state is just kind of, you can almost think of it as like the mean conditions, right? And so for our three unknowns here, Q, A, and pressure, right? QA and P, we have to define kind of, you can think of them as almost like default values or mean values. Okay. Right. And so if we do that, we're going to have Q, right? So its default state or reference state will be given by Q naught. And so this is like our reference flow rate. P will have a reference state of P naught, and so this will be our reference pressure. And A will have a reference state A naught, okay? And so this is like a reference. So A here is our only geometrical parameter, so I'll call this our reference geometry. Okay. But it's really kind of the cross-sectional area of the vessel, okay? And so the reasons we wanted to find a mean state or a reference state here is that we can, now that we have a reference state, we can kind of reframe the equations above. And so when you establish a reference state like this, what you can say is that the equations above will tell us how much we deviate from this reference state. Okay. Okay. And so we're no longer solving for, just Q by itself or P by itself or A by itself. What we're solving for instead are, what are the deviations in these quantities from our reference state? Okay. Right. So this is a pretty common trick that is used in applied math to kind of help us solve the equations. Okay. And this only works if you assume that the deviations from your reference state are going to be fairly small. Okay. Right. And so we're basically making a gamble on our physical system to say that, we have these 1D equations right here. We have this reference state. We know that all of these quantities are going to vary. So we know that Q is going to vary, P is going to vary, area is going to vary. Okay. But we're making the assumption, we're making the gamble that, these deviations are going to be fairly small, right? And so Q, if you define Q naught to be like this line right here, okay, then the actual Q might look something like this. Okay. Right, but these deviations are going to be fairly small. So everything is going to be roughly around your reference state. Okay. Okay. Where this deviation, now what we're solving for, this deviation from the reference state, this is now what we're solving for as Q in our equations. Okay. So that was kind of very applied mathy. So that was no sacrilege this time. This is real math. But I think it's probably this is a little bit, this is kind of creeping into graduate level kind of logic in these equations. So are there any questions on any of this? Okay. All right. And so what is that bias? And so small deviations is great, because what we could say is that if all of Q, A, and P, if all of these are small, okay, then their products are going to be even smaller. Right? So think of a small number. So think of a number like 0.01, right? That's a small number. When we take 0.01 squared, right? So we multiply by itself, we end up with an even smaller number. So we end up with 0.0001. Right? And so the logic is that if you can reframe your equation such that everything is small, then anytime you have a product of things, then that ends up being even smaller. And when things are even smaller, we can eliminate them from the equation. Okay, so let's go back up to our 1D equations right here, and let's go ahead and eliminate some terms based on that. Okay. All right, and so the only term that we're going to eliminate is mostly this term right here. Okay. And so in that term, you can see we have Q squared. And so, Q squared, if our deviations in Q are small, then, Q squared is going to be an even smaller number. Okay. And when we take the derivative with respect to Z, which is, down the center line, then that's going to be even smaller than that. Okay. All right. So that's one term. That's one term down. For these other two terms, we're going to keep those terms. We want to keep those terms in our expression because, first of all, this second term here, this has our pressure, right? And so it's the only term here that has pressure. And so we want to make sure that we keep that because, we are interested in the pressure wave propagation. So we want to keep that term. And the second term that I've circled here, it's one of the only two terms that has viscosity. And so remember, we're talking about impedance. And so a big part of impedance is going to be the viscosity of the flow. And so we want to make sure we keep that one as well. And so those two we're going to keep. But the way that we're going to make those terms linear, okay? And so for the terms that we keep, okay, what we're going to do is that instead of using A, we're going to use the reference geometry. Okay. Okay. And A naught is a constant. Okay. And so by plugging in A naught into those equations, and for A, we turn those nonlinear terms into linear terms. Okay. And so that'll work for us. All right. And so if we apply all of those changes, we get partial A, partial T, plus partial Q, partial X. Okay. That's our conservation of mass. And so nothing changed with that. Okay. right? In our other equation, we have partial Q partial T plus A naught over rho, partial P partial Z, okay, is equal to minus 8 pi nu Q over A naught plus nu partial Q partial squared Q partial Z squared. Okay. Okay. And so we're all linear here, and so we're all and so we are good to go. So we're almost actually we're almost good to go. Okay. We're going to make one more assumption just to make this a little bit simpler, and the assumption that we're going to make is that we have two viscous terms here, right? So we have a viscous term which is an 8 pi nu Q over A naught, and we have another viscous term that takes a derivative along the centerline direction. Okay. And so what we're going to do is we're going to eliminate the second one right here. Okay. And the reasoning for this is that we're going to assume that when we take the streamwise or the path line viscous effects, that's going to be insignificant compared to the other direction. Okay. And so that has nothing really to do with the linearization, but that's kind of a reasonable assumption that we make in general for these kinds of flows. Okay? And in fact, if you look back to our fluids review when we solved Navier-Stokes, you'll see that we did something very similar where we eliminated that streamwise direction. Okay. And so through all of those, through all that linearization, through all that simplifying, we end up with these equations right here. All right. Any questions on any of this? Okay. Yeah. So this kind of manipulating equations and making assumptions, this kind of falls under the category of analytical methods. And it's you can see it's much more of an art than it is a science. And so I think when people think of like equations in math, they think of things are very cut and dry. You plug in, you get one answer. But there's a lot of art that goes into in terms of things like linearizing these equations and putting them in certain ways, assuming terms are a certain way or not, which is really cool. And I wish I was better at this. This is probably the limit of my analytical abilities. But if you ever bump into Dr. Sanders, you should ask him what he does for his research. And it's fascinating, and I think people that do analytical work, I think are they have a lot of respect from people in the community, just because it's not the same as just running a simulation or running an experiment. You really have to think really critically. You really have to really do a lot of think outside the box with the mathematical tools that you have available, and it's impressive. It's cool. Okay. All right. And so, once that we have these equations right here, the best part is that these are linear. And so we can actually start to solve these now. Okay. Okay. There's still partial differential equations, and so there's still PDEs, and so it's not going to be easy to solve it, but we can actually start to solve it. Okay? And what we'll see eventually is that once we kind of massage these equations a bit more, they'll give us a very classical equation. Okay? And the equation that we'll get is the very classic damped wave equation. Right? Probably you guys have heard of wave equation before from your physics class or something like that. I don't know if you solved it or not, because it's a partial differential equation, but you probably know that the wave equation exists, right? And so these equations right here will actually give us those wave equations, right? And that's really cool because remember the reason that we're doing this is so that we can better understand wave propagation. Okay? And so I think this is kind of the part of the class where it kind of makes sense. Why are we even calling these pressure waves to begin with? And so what is a pressure wave? And so by looking at these equations, you'll really start to kind of understand what that really means. Okay. Any questions on any of this? Okay, so let's go ahead and continue. And so, before we kind of continue on, let's define a new term. And so let's go ahead and define a parameter that we're going to call the wave speed, right? Since eventually, we're going to be solving the wave equation, it makes sense that we have an expression for that wave speed. So let's go ahead and define. And so we'll call that C naught squared. Okay, so C naught squared is going to be our wave speed. It's going to be A naught over rho times partial P partial A. Okay. Right, and so what we're basically saying is that the wave speed is going to be a function of the cross-sectional area. Okay, it's going to be a function of the density, and it's going to be a function of how the pressure in the vessel varies as the area itself varies. Okay. Okay. And so what we want to do, and so I know a lot of this proof is very unfortunately it's very hand wavy, and it kind of seems like I kind of magically know what's going to happen in the next step, and so it's not the most satisfying proof, I know, but what we want to do is that we want to use this in our conservation of mass equation. Okay. And in particular, the term that we're going to incorporate into is partial A, partial T, right? So if you look back at our conservation of mass, we have this term right here, partial A, partial T, right? If we look at our expression for the, for the wave speed, you can see here that we have a derivative that involves A. And so that tells us that, maybe we can have an expression here that depends on, that can be manipulated to get partial A, partial T. Okay. And so to that end, let's take partial A, partial T, and let's expand it using a chain rule. Okay. And so we have partial A, partial T. Okay. What we can say is that this is equal to partial A, partial P for pressure times partial P, partial T. All right. And so this term is really interesting here because it looks like the inverse of this term right here, right? And so what we can say is that if we incorporate this top equation into here, if we kind of flip everything over, then what we can say is that partial A, partial P is equal to A naught over rho C0 squared. Okay. And so if we plug that in, then what we get is that partial A, partial T is equal to A naught over rho C naught squared times dP dt. So this is the reason why I wish I was better at analytical methods, because I know a lot of like literally the last 3 steps that we just did, it kind of seems like I just came up with them by magic, right? And so it didn't really follow logically from where we were, right? And so the best proofs that are out there are the ones that kind of follow logically. So basically that you get this, and so now that we see this, then we know that we need to do the next step. Here we kind of are looking ahead a little bit. So we're kind of looking ahead of where we want to be, and we kind of manipulate the equations in order to get there, which is a fine way to do a proof as well. But I think when you're looking at it for the first time, it can be very confusing. Okay, but let me give you that context. And so the reason we're doing this, and so basically we're going to substitute this in for partial a partial t. Okay, the reason we're doing this is so that we can eliminate a from our equations. Okay. Right, and the way we're going to do that is by replacing every time we see a with some expression that involves the pressure. Because remember, our goal for this is some kind of wave equation for the pressure itself. And so, by eliminating a and introducing pressure into this, then that'll help us get us closer to that wave equation that we so desire. Okay. And so if we plug this expression into conservation of mass, then we have a new expression for that. Okay. And so our conservation of mass equation now becomes a conservation of mass equation now becomes a naught over rho c naught squared partial p partial t. Okay, so we've eliminated partial a partial t plus partial q partial z is equal to 0. Okay. Okay. Any questions on any of this? Okay. Okay. And so now that we have the equation in this form, let's go back to our linearized momentum equation. Okay. And so let me go ahead and write that down first, since we have partial q partial t plus a naught rho over partial p partial z is equal to minus 8 nu pi q over a naught. Okay. All right. And so we have 2 equations here. We've eliminated a, or at least the unknown a, right? We still have a naughts, but remember a naught is a constant. Okay. And so we have 2 equations here, and we're gonna solve them for our 2 unknowns. So we're gonna solve them for q and for p. Okay. But unlike an algebraic equation, this is not just a simple matter of kind of just solving one, plugging into the other, or doing some kind of matrix expression. So we have two couple of PDEs here, which make it difficult. Okay. And so the way that we're going to solve this is that we're going to solve for one first. Okay. And so the one that we're going to solve for first is going to be q, because q it appears here in a little bit more complicated form than the p, right? And so we have derivatives of Q with respect to Z, with respect to T. And we also have this Q that's appearing on the outside right here, okay? And so Q is going to be a little bit more complicated to eliminate. Okay. And so I know ultimately our goal is to solve for P, but Q is kind of in the way right here, and you know, and we're kind of running out of cute math tricks that we can use to get rid of those things, right? We've done a lot of those kind of tricks already, right? And so actually the best way to actually get to P is to actually solve for Q first and then plug that back in, okay? Because if we look at how P appears in these equations, it appears in a lot less complicated in a way. Okay, so if we look at the conservation of mass equation, we have partial P, partial T. And in the momentum equation, we have partial P, partial Z, right? And so in both equations, the pressure only appears once. Okay. And that's great because, you know, that will help us, you know, it'll make it a lot easier to eliminate. Granted, their derivatives are different. And so one of the derivatives is in T and one of them is in Z. You know, but we can work with that. That's a lot easier for us to eliminate than Q, where it appears in lots of different forms. Okay. All right. And so we're just about out of time. And so, you know, there's quite a bit more that we need to do. And so let me just kind of give you a sneak preview of where we're going, and then we'll wrap it up for today. And so what we're going to do is that, you know, we need to make these we need to make these two P terms have the same derivative. Okay. Okay. And so the way we're going to do that is we're going to take our continuity equation, our conservation of mass. We're going to take the derivative of this entire expression with Z. Okay, so we're going to take partial Z across the whole thing. And then for our momentum equation, we're going to take the derivative with T. Okay. And so we're taking different derivatives on the two equations here that are different than the P derivative. Okay? Because when we do that, we're going to get a mixed derivative. And so we're going to get partial squared P, partial Z, partial T. Okay. But that's going to show up in both equations. Okay. And that's great because, you know, then if they show up in both equations, we can manipulate this algebraically to eliminate them. Okay. And once we eliminate that pressure, then we're just going to have one big equation to solve for Q, and we can solve for Q from that. Okay, so that's where we're going. And so, you know, unfortunately, we have to take the spring break. And so, you know, this is going to be a lot of details to remember after the spring break, but I'll try my best to kind of recap after that. Okay. All right, any final questions on any of this? Okay, all right, and so that's it for today. So thank you guys for tuning in. Hope you guys have a great spring break. If you guys are going to be working on your projects over spring break, I will be available. And so I'm not going anywhere. I have too much work I need to do. And so if you have any questions on the project, just reach out to me, and we can set up a Zoom call over spring break. Okay. All right. So thank you, everybody. I'll see you in a couple of weeks, and try to rest a little bit. Yeah. We do a midterm exam, but it's going to be like a pseudo final. So it's going to be in week 14, I think. Okay. And so it's like a kind of a final before finals week. Okay. What do we do for a final? It's just the final project. Oh, it's yeah. Yeah, so I don't like having final exams and final projects. I mean, first of all, it's way too much for me to grade, but I think it's also kind of way too much for you guys to do too. So, you know, I always told myself I'm gonna do a final project, then no final exam.
You're wise beyond your years.
Okay.
Wait, what?
What is your Discord profile picture?
Oh, it's the main character from no. Everyone thinks it's Evangelion, but it's from a game called The Legend of Heroes: Trails in the Sky. It's an older game. It's more niche. I love that series. There's nine games that are localized in English. And so I played all 9. I loved all 9 of them. But I've never gotten a single one of my friends to play it because each game, there's 9 games and each of them are like 80-hour JRPG games. And so
We have a spring break.
don't maybe over summer you should start.
Okay. Okay. Hello?
All right, David, any final questions before I wrap up the Zoom? Oh, no, I can't. Yeah, whenever I unmute, then it turns the screen. Although I guess we're done. So let me unmute. Okay, try again, David.
You hear me now? Hello?
Oh, yeah, I can hear you. Yep.
Okay, cool. I was breaking out for a bit.
Yeah, the audio in here is messed up because I can only unmute if the projector's off. It's weird.
Okay, cool. Oh, can I share my screen real quick?
Yes, let me stop sharing here.
Okay, thank you.
Hey, David, why you so bad at Clash, man?
You're getting some comments from the peanut gallery, David.
Yeah, I can tell. Can you see this?
Yes, yes.
Okay, cool. I was just wondering, I was kind of following from your lecture, but I don't know. I'm trying to figure out. I get the first one. I'm just trying to figure out the second one.
Yep.
Do we incorporate QL? Would we incorporate QL in that?
You do.
For C1?
Yes, and so you would have to do a conservation of mass. And so right at the junction PC2, you can see that QL is going to split, right? And so it's going to split some into the upper branch
Okay.
and some into the lower branch as well.
Okay.
Oh, actually, no. So I'm sorry. So for the upper branch, you can find the Q that goes into that from the 2 pressures, right?
Okay.
Since you have the resistor R1 and you
Uh-huh.
have the difference in pressure PC2 minus PC1, if you do PC2 minus PC1 over R1, that would be the flow coming in, right?
Okay. And
Um,
then for the out, I have this. Does that kind of looked? 'Cause then I did CTP C1 DT plus PC1 over R2.
yep,
This is kind of
that
split.
should be right. So this
Okay.
this expression here is good. The only thing is that there's no QL for this one because the
Okay.
Q that's going into there is exactly PC2 minus PC1 over R1. And
That
so
makes sense.
And so that equation that you have minus the QL1,
Uh-huh.
I'm covering up with my finger as if you can see it. And so I know you can see it. But that equation right there, that's exactly what you need. And so if you manipulate everything kind of on the right of QL of that, then you're going to get the equation just fine.
Okay. Okay. I appreciate it. Thank you very much.
Yeah. Mhm.
Thank you. Have a good break.
Thanks, you too. Sure. What's up?
Is that on the MATLAB code?